Hi guys, welcome back to Data Every Day. Today we're looking at a dataset of marketing campaign subjects where each one of these represents a customer or subject who was participated in this marketing campaign, and we're trying to predict if the campaign was successful or not based on the response column at the end. So 1 means the customer accepted the offer and 0 is otherwise. So let's hop into the notebook. We're going to be using NumPy and Pandas for working with the data. For visualization, we'll use PyPlot and Seaborn. And for pre-processing, we'll use the train test split function and standard scaler from sklearn. Just zoom this up a little. And we will be using TensorFlow to train a neural network today to make our predictions. For analyzing the results, we'll use the confusion matrix and classification report from sklearn. So let's go ahead and import all of that, and we can load in the data using pandas.readcsv. And we can get the CSV file path up here. We're going to be using the CSV file, not the Excel file. So let's go and copy that, paste it in, and take a look. And immediately we can see all of them have landed in the same column, and this is because we're using the wrong delimiter. So by default, a CSV file is comma-separated values, but sometimes you'll have the value separated with a different character. In this case, it's a semicolon. So up here, we're going to go in and type delimiter equals semicolon. And now we can load it in properly. So let's get a little more information on the dataset with data.info. I'm looking for null values mainly here, and it looks like I do see some in income, but not very many, only 4. We can double check this with data.isNA.sum to get the number of null values in each column, and there are only there's 24 null values in income, but all the rest are good. So let's start pre-processing. I would also like to point out we have 3 object columns, which are this one, and the date column, which we will have to encode properly. So let's start and create a pre-process inputs function that's going to take in a data frame. It's going to make a copy of the data frame, and then it's going to return that data frame. Right now, this is just going to create the copy of the data that we're going to perform our pre-processing on, and then I'm going to call that x. So x is going to be pre-process inputs of data, and currently x is just a copy. So first thing I want to do is drop the ID column, because the ID column is not going to give us any useful information for predicting the response, because these are all different for each example. So drop ID column. For this, we can use df.drop ID from axis 1, since it's the column axis, and you can see it's gone. Alright, so I guess next we can deal with the dates. Actually, you know what? First, let's fill the missing values for the income column. So fill missing income values. Since we really don't have too many, and it's a numerical feature, it makes sense to fill it with the mean of the column. So with column mean. And so for this, we can take the income column and call fill NA on it. Fill NA allows us to fill the missing values with whatever we pass in here. And we're going to pass in the mean of the column. So df sub income.mean, and then we're going to store that whole filled in version of the column back into the column name. And we can see, well, we actually can't see it, but if we check .isNA on x, if we sum over the matrix twice, so if we look, .isNA returns a true-false matrix, where a true means there's a missing value there. So if we sum over all the trues in both the rows and the columns, we'll get the total number of missing values in the whole data set, and that is 0 now. So we're done with missing values. Let's do the date encoding. Not data, date encoding. And so here's our date column, DT customer. If we take this column, I'll do it for x. Let's say I wanted to take out just the year, because I mean there's a few ways we can encode this. One would be to rank all the dates in terms of recency, and then sort of just make it a single continuous column. we actually already have a feature here that may be a measure of that. So first of all, it may be redundant. Second of all, we lose a lot of information from the date that way, because we fail to capture the cycles that are contained within a year. For example, month is very useful for knowing temperature. I mean, I'm not sure how useful temperature would be for a task like this, but there is information in the month that you can't get if you just rank them all as a measure of recency. So let's say we want to take out the month. Now we could do this with regular expressions, and if we know that all of these are the same length, we could actually just do it by indexing. We could apply a function to this column that takes given x, which is one of these strings, and just takes x evaluated from, I think it's like, was it 5 until 7? Yeah, and that gives us just the months. But slicing the x, you know, it could work, it definitely could work, but we want a way that's going to work even if the data is not entered properly. So there's this function that Pandas has, which is toDateTime, which can just convert the whole column into a datetime column. And what's nice about this, if we copy in the column here, it looks the same, but you can see the data type is now datetime64. Before it was object. Now we can apply a function. And instead of having to slice x, x is now a datetime object. We can actually just call, take the attribute x.month, and that will return the month, and it will do it as an integer, so we don't have to turn it into an integer afterwards. So this is the way we're going to do it. We're going to convert the column to a datetime column, and then we're going to extract the year, month, and day out of the column. So let's take it's called DT customer, date customer, and set it equal to the same thing, but as a datetime column. So pd.toDateTime of the column. Then what we'll do is go and take out the year. We'll call it year customer, and that's going to be the original column with a lambda function applied. And now since it's datetime, we can just get x.year for each element x in the column. And then we'll do the same thing for month and day. So this one's going to be month, and at the end here we just change it to month. And this one is going to be day, and at the end we just change it to day. Then once we've done that, we can just drop the original DT customer column, since we extracted all the information we need out of it. So we drop it from axis 1, and we can take a look. Okay. So now our date column is gone, and at the end we have the year, year, month, and day of the customer's participation. And these are as integers, so we don't have to worry about that. The last things we have to worry about are these guys, education and marital status, because they're the last string columns in the whole dataset. Everything else here is numeric, continuous features, and you can see it looks like there may be some categoricals that were encoded. I'm not exactly sure. We can check over here if a customer accepted. Right, so it's a 1 or a 0. These are binary features for each campaign. So I don't know if you consider them categorical. No, it'll probably be like a yeah. Okay. Anyway, everything is encoded. These are some count columns. What is the MNT? This is the amount. So the amount of things, that's also continuous. Looks like the only thing left to deal with are these, the education and marital status columns. And if we look at, let's look at the unique values in each. So, well, we should really look at the length of unique values. We want to know how many values are in there. So let's take marital status. No, not the full column. I want to get the unique values and then see how many we have. So there's 8 values in this column. And let's check education. Alright, there's 5 values in this column. So they're both candidates for nominal encoding or one-hot encoding. Now, some people might argue that education can be ordered, that the values in them can be ordered. But even if we could rank these, which I suppose you can, how would we encode it? It's a bit strange to say, okay, well, graduation, basic is 0, then graduation is 1. Where do we get this idea? I mean, especially once we get if we take master after that, how can we say master is 2? Where's the spacing between those numbers come from? We just made it up, and it doesn't really make sense. It's a bit it's not the best way to encode it because we're sort of putting our own information in there. Now, if we were doing something like month is an example of when you can use ordinal encoding, when you can space them, because we know every month is roughly the same spacing from each other. If you know the spacings of your values in some like meaningful way, then ordinal encoding is good. But if you don't really know, even if there is some sort of order, if you can't be sure how to space it, we should do nominal or one-hot encoding. For this, we'll use getDummies from Pandas, and we'll grab the column, paste it in, and you can see that each unique value now has its own column, and a 1 in a given location will represent the original value of that example. So here, example 0 has a 1 for graduation. All that means is up here, the value for education is graduation, for example 0. So we can also include a prefix here. We can make it the same as the column name if we want. And that will just add education to the beginning of each column so that we know where these columns originally came from. And I'm showing you this is because I want to create my function up here, one-hot encode, that takes in a data frame and a column. First, I'll create a copy of the data frame, and then we're going to paste this in. So I just want to change this now. X is going to become df, and the column name is going to become column, and the prefix will also be the same as the column name. And I'll store this in dummies. Those will be the dummy columns. Then I want to take our original data frame and concatenate together the original data frame and the new dummies side by side, so axis 1. And then once we've put them together, we can drop the original column from which we created the dummies, since we've taken out all the information we need from it. And there's our function. So in here, one-hot encoding, we're going to take we'll just take the two columns, education and marital status. Say for each column in education and marital status, we will call one-hot encode. Sorry, it's so df equals one-hot encode, passing the same data frame and the column that we're on. I'll say column equals column. Alright, and now we look at this. Oh, we got a problem. Oh, I wrote marital status. Alright. Now all of our data is in numeric form. At the end here, we have our education dummies and our marital status dummies. And you can see the original column name on as the prefix so that we know where these are coming from. And then all the rest of our data is already there. So if we look at if we want to see how many more object columns we have, we can do select D types object, and you see there's no more columns, 0 columns. So our data is fully encoded as numeric data, and there are no missing values. So we can proceed to split and scale the data. So first, split the data. We're going to split df into x and y. Y is going to be the target. X is all the feature data that we're using to predict the target. So y is going to be df sub response, since response is the name, all the way at the end here, the name of our target column. So we're storing that column into y, and then x is going to be df.drop response, since we want all the rest of it, and axis 1. Then we'll do our train test split. So now I want to separate 70% of the rows into the train set and 30% of the rows into the test set. For this, we can use the train test split function from sklearn. We want to specify what we want to split, which is x and y, then give it a train size, how much of the data is going to the train set. We'll say 70%. Then we will include shuffle equals true. This is on by default, but basically this function will shuffle the data before it makes the split. which is nice, so we don't have to do it ourselves. And because it's doing shuffling, let's include a random state so that it's always done the same way when we run this notebook. And now this will return 4 new sets of the data: xtrain, xtest, ytrain, and ytest. And let's return these 4 sets down here. So that's going to be the output of the function. We'll get them back over here. And let's take a look at xtrain. So here's xtrain. Currently it does not have the response column anymore. And everything, this is only 70% of the data. Xtest contains the other 30%. And our y's, ytrain and ytest, our y's contain the labels 0 or 1. Remember, where 1 means the response was positive, that the customer did go along with the marketing campaign. Okay, so alright, so let's look at that. Let's scale the data. So right now all the ranges of each column the range of values in each column is very different. We have really high values in the income column. We only have 0 and 1 in this column. They're all over the place. The means and the variances are all over the place. So by scaling the data, we can ensure that the range of values in each column is the same. And that can really improve the performance of many models, especially neural networks, which we will be using today. So let's go ahead and create a scalar object. And we're going to use a standard scalar from sklearn. And the standard scalar will give each column a mean of 0 and a variance of 1. So it will perform a shift and a scale to each column to standardize all of the columns. And we'll fit the scalar just to the train set, because we sort of want to pretend we don't have access to the test set at the time of pre-processing. So we fit it only to the train set, and then we transform both xtrain and xtest using that fit. So we do it with scalar.transform xtrain. Now I would like to point out that this returns a NumPy array. So if we run this, the data has been scaled, but you can see we can't see it as a nice Pandas series anymore. So let's turn it, data frame. So let's turn it back into a data frame with pandas.dataframe. And because we're reconstructing it, we want to include that the indices should be the same as they were before, and the column names should be the same as they were before. Then we'll grab this whole line, duplicate it, and change all these to xtest. So again, we're fitting only to the train set, but transforming both the train and test set. Alright, and here it is. So here's our finished scaled data set, and if we look at the mean of each column, you can see they're all very close to 0, and the variances are all very close to 1. Our y's have not been scaled, they are still our label values. So now let's start training. So I'm just going to do a simple 2 hidden layer neural network using TensorFlow, Keras actually, which is a high level library on top of TensorFlow. It makes building models really easy. So inputs, that's our input layer, is going to be tf.keras.input. And the shape of the input, this is going to be a vector of our features for a given row. So imagine a single one of these training examples coming in as a row. How many inputs is it getting? Well, it's getting however many columns we have. That's 40. So we can double check this with xtrain.shape. That is rows by columns. So this is the number of inputs coming in for a given example. And we can get that with shape sub 1. So let's take that and put it in here. And we'll put a comma to denote it's a vector. And then we'll create 2 hidden layers. I'll just call it x. This is using the functional model building from Keras. So the first hidden layer is tf.keras.layers.dense. We'll give it 128 neurons, a ReLU activation function, and we'll pass in the inputs. Then we'll duplicate this layer, except we pass in x, so it flows through. Then finally we have our outputs, and this is tf.keras.layers.dense. We output a single value, and this value is the probability for our positive class. So It's going to output a probability, and because we need a value between 0 and 1 for a probability, we're going to give it an activation of sigmoid, and we'll pass an x here. Then we'll create the model with tf.keras.model. The inputs are specified as inputs, and the outputs are outputs. Alright, we have our model. Let's compile it with model.compile. We want to specify here an optimizer to use. We'll use the atom optimizer. For loss, we'll use binary cross entropy, or log loss, which is great for binary classification tasks like this. And then for metrics, I'll use both accuracy and AUC. So tf.keras.metrics.auc, which is the area under the receiver operating characteristic curve, and it's a better way of gauging the performance within classes when you have a class imbalance. And I believe we do have one today. Not terrible. It's not like a really, really small positive response, but you can see, yeah, it is quite imbalanced. So it's nice to see how we're doing with that in addition to accuracy. Then we will fit the model using model.fit, and I'll store the results in history. Then we're going to fit on xtrain, compare those results to ytrain. We'll give it a validation split of 20%. The other 80% will be used for training. And then a batch size of 32. And we'll train for a lot of epochs, 100 epochs, and include a callback function, which is tf.keras.callbacks.early stopping, which will stop the model for us when it notices that it has stopped improving. So we can monitor the validation loss like this, and specify a patience value, which says how many epochs are you willing to wait before you stop the model. So let's say 3. And so this is going to look at the validation loss after every epoch, and when it stops going down for 3 epochs in a row, it will stop the model, and it will restore the weights from the best epoch. So I'm specifying restore best weights equals true. Run that. This should train very quickly. Alright, and you can see we're doing quite well, 89 to 90% accuracy, and the AUC is quite good. So I don't know, we'll have to see how it actually is doing with a confusion matrix. So that's what I'd like to do next. Let's get the results, and let's first evaluate the model on the test set. So at this point, we still don't know how it will do on completely unseen data. So results is going to be model.evaluate xtest ytest, and verbose I'm setting to 0. Then we'll print out the loss, test loss. We'll display the loss to 5 decimal places and format that with results sub 0. So model.evaluate will return 3 values because we specified 2 metrics. First it returns the loss, and then it returns whatever metrics you specified. So here results sub 0 will be the loss, results sub 1 will be the accuracy, and results sub 2 will be the AUC. So let's copy that over. This one will be AUC, and we'll format this. This will be results sub 2. This one will be accuracy. For accuracy, I'm going to display it to 2 decimal places and as a percentage, because it's meant to be interpreted actually as a percent. And then we will pass in result sub 1, and I'll multiply it by 100 since we're working with a percentage there. Alright, let me just line these up. Okay. And here it is. So you can see we're doing alright on the test set, 89%. But to get a better sense, because we have a class imbalance, I would like to see a confusion matrix. So let's create a set of predictions, which I'll call ypred, and this will come from model.predict on the test set. So we pass in xtest to model.predict. Now I want to point out that if you run this, it returns probability values, the actual output of the sigmoid activation. So if we ask if it's greater than 0.5 in a given location, then true means yes, it's greater than 50%, then false is less than 50%. And so this is the same as making our classifications, right? Now, we can turn this, it's already a numpy array, but we can call numpy array specifying the data type as numpy.int. In order to turn this into zeros and ones, which will line up with our y test. So now they'll be able to be compared. So I'm going to grab this and put that in here. That will be our predictions. And then we'll create a confusion matrix, which I'll call CM, using the confusion matrix function from sklearn, and we can pass in ytest and ypred for classification report. So this is a way to sort of analyze the confusion matrix more nicely without having to calculate the precision and recall values yourself. So for this, we'll pass in ytest and ypred as well, and specify some target names. Target names are going to be the names of our classes. Because this is a response variable, it's just going to be failure and success, like that. Alright, then we'll plot out the confusion matrix with Seaborn and pyplot. So we'll create a new pyplot figure. We'll give it a figure size of 6 by 6 since it's a square. And we'll call seaborn.heatmap and pass in our confusion matrix. Then we'll turn on annotations. I'm going to format it with G. This just ensures that we see the counts as integers and not as scientific notation. Then set the minimum value, minimum color value to 0. Specify the color map, which can be blues, and then turn off the color bar. And then I'm going to give it some tick marks. So on the x-axis, we want tick marks that are spaced evenly. So we'll use numpy.arange for the ticks. And the arange is how many values we want. In this case, there's only 2 classes, so just 2. And I want to shift them over by 1/2 so that they end up in the middle of each box. Then the labels is going to be the same as the target names. That's what's going on the x-axis. I'll do exactly the same thing for the y ticks. Alright, and then we'll give it some axis labels. So on the x will be the predicted values, on the y will be the actual values, and then the title of the plot will be confusion matrix. Alright, and we'll show it and print out the classification report. So pass in CLR, and let's take a look. Alright, so here is the confusion matrix, and you can see, yeah, we're not doing so bad, but we're also not doing so well. We are not getting as many in the true positives as we'd like. So you can see our F1 score for failure, which is this class, is quite good. We have 0.94. Both precision and recall are really high. But for success, which is this class, we have a much lower F1 score. Now it's still not terrible. It's still decent. We might want to address the class imbalance if we want to improve this model. We can see that the recall is particularly low. And the recall is a measure of out of all the actual success examples, meaning these 2 boxes, both the ones we predicted as failure and as success, but all the actual successes, only 56% of them we got right. So 56% of these values lie in this box. The precision means out of all the ones we predicted as success, whether they were or they weren't, then only 73% of them we got correct. So out of these 2 boxes, we got 73% correct. And the F1 score is sort of a combination of the 2. It balances precision and recall to give us a one value metric. Alright, so there you have it. So that will sum up today's video. Thank you so much for watching. I hope you enjoyed it. If you did, make sure to subscribe and hit the bell for more content, and leave any comments you have in the section below. I'll see you guys tomorrow. Have a fantastic day.